Okay, since we'll all come back, so we can get started. We are still about 2 minutes early, so we can give Lucy two more minutes. Our next speaker is Professor Lucy Po from University of Colorado at Boulder. And Professor Paul received all her degrees from Stanford, I believe in electrical engineering. And she has won many awards, and she's currently a fellow of IEEE and IFAC. Let's welcome Professor Paul.
Thank you very much. Well, it's an honor to be here. Thank you for inviting me, and I'm sorry I missed yesterday. I'm glad I finally made it. As mentioned, I'll be talking about some of the opportunities and challenges of integrating ever more wind and solar onto our power grids. So I'm from University of Colorado, Boulder, and these are some aerial photos of our campus, and a larger aerial photo is shown here. So if you've never been to Boulder, I welcome you to come visit, and do let me know. I'd love to show you around. We are at the foot of the Rocky Mountains. So this is our campus here. When we look west, we see the mountains. When we look east, we see a lot of plains. All right, so what I'm going to talk about today is first, I'll overview power systems and talk about the fact that we have ever increasing demands for electrical energy. And then I'll talk a little bit about where we are with wind energy and solar photovoltaics, and how these are just excellent opportunities for clean energy, for fighting climate change, and for meeting our increasing demands for electrical energy. Then I'll talk about why having more and more wind and solar causes challenges for the grid, and I'll talk about one particular solution idea that we are actually trying to address in the wind energy area, and then I'll end with some concluding remarks. All right, so power systems. So this is a very high-level overview of power systems. So historically, we have a power plant providing power to its local customers, and this is happening in many different locations geographically. Now, traditional power plants have large synchronous generators. These are these large electromechanical machines, and now over time, customers and power plants have all become networked together into what we now call our power grid. Now, when we have synchronous generators that are networked together and they're spinning at nearly the same frequency, they will tend to synchronize with one another. And that's a good thing for grid stability. Now, on the other hand, if we have a particular power plant that, say, has a fault and has to be taken offline, then suddenly we have a large discrepancy locally between the power generated and the power demanded that leads to frequency fluctuations, which can propagate across the grid and destabilize the power grid, leading to blackouts, which of course we want to avoid. So on the grid, we want power generated and power demanded to equal. And the frequency fluctuations on the grid are governed by the so-called swing equation, and this is the simplest form of the swing equation. So PG is the electrical power generated, PL is the load power or the electrical power demanded. And so this is a fun slide that my PhD student made up for me a few years ago. I've used it many times. I think it's a fun, easy way to try to remember when grid frequency increases and when grid frequency drops. Okay, so we want the electrical power generated and the electrical power demanded to be equal. In that instance, then the grid frequency remains constant at the desired frequency. So here in Hong Kong, that desired frequency is 50 hertz. This 50 hertz in China and Europe. In the US, the desired frequency is at 60 hertz. So when load and generation are equal, Mr. Conventional generation bear is pedaling along at a constant frequency. Now, when the demanded power suddenly increases relative to generation, then grid frequency will drop. Okay, so if Mr. Conventional generation bear applies the same power to the pedals, he's going to slow down. Now, conversely, when the demanded power suddenly decreases relative to generation, then grid frequency will increase. All right, so we want demanded power and generated power to be equal. And this is traditionally done by the utilities controlling the power generated to follow the time-varying load. Now, this can be done relatively well as long as there are enough operational reserves. We can't have every single power plant be operating at maximum capacity. We have to have enough operational reserves so that the power can be increased or decreased to follow that time-varying load. Now, if there's imbalance, then that will lead to frequency variations, and we need to control the frequency to quite accurately about that nominal frequency. So typically in most regions around the world, we need to control the frequency to 1% of the nominal frequency. If we have too large of an imbalance and that leads to too large of frequency fluctuations where we go outside those thresholds, then that will lead to catastrophic events leading to blackouts, which we want to avoid. Okay, so if we take a look at a typical load across a 24-hour period, so across a day. So in the wee hours of the morning, there's very low load. So everybody gets up and business is open. There's higher load. Usually there's a second peak at the end of the day. People go home. And then the load will drop back down at night. So utility might meet this load perhaps with some nuclear power. Often there's some amount of coal. There might be some hydro. And what's usually cycled up and down to meet the varying load is natural gas. Now, what are some typical demands we put on the system? Right, so the load consists of industrial loads as well as individual customers' households. So large industrial factories with extremely large loads, usually they are in communication with the utility. They have some plan of when they're going to be really drawing large amounts of power. So the utility can then plan for those. But you and I, we don't call the utility when we're going to plug in different things. Okay, so what are typical loads that we're demanding? Usually we just use whatever we want to use and we don't worry about it. But what are you actually demanding from the grid? Okay, when we use our mobile phones, when we're actually actively using our mobile phones, we're typically drawing about 1 watt from the battery. Now, when a mobile phone is actually plugged into the wall, it's actually drawing probably about 10 watts. Now, laptop, okay, when we're actively using it, we're probably drawing about 10 watts from the battery. And again, when it's plugged into the wall and it's being charged, it's probably drawing about 100 watts. Now, TVs, depending on the size and the particular technology, plasma, LCD, and whatnot, there's some variation. But typically, it's drawing about 100 watts when it's on. And then we have a number of appliances in our household that, when they're actively being used, draw about 1 kilowatt. So a typical household draw for power is, on average, about 2 kilowatts. Usually, you have maybe one of these appliances actively being used and a number of other things, including lights and such. And so you're drawing about 2 kilowatts. If you have many appliances on at the same time, you probably have a much larger than average load. Now, more and more people are getting electric vehicles. Now, if you haven't done any changes to your house and you're just plugging into the normal wall outlet to charge your vehicle, you're probably just drawing 1 kilowatt. Then it takes a very long time to charge your car. Most people who have electric vehicles will change the configuration of one outlet so that they can charge faster. And in those cases, they're drawing about 10 kilowatts when they're charging their vehicle. Now, if you go to a supercharging station, which are being built in a number of cities, and you plug in there, you're drawing about 100 kilowatts. So as there are many supercharging stations being put up, and more people have electric vehicles, and they go to these supercharging stations, and they all plug in about the same time, that is suddenly a very large demand on the grid. Okay? And it's unlikely that you're going to call the utility, right? So these are unpredictable increases in power that then the utility has to be able to provide. All right, so we have ever more increases in our demands for electrical power. And luckily, wind and solar PV are being developed quite well that they can now meet this ever-growing demand. Okay, so let's take a look at wind first and see where we are there. Okay, so the installed capacity of wind power is growing quite healthily. And so if we look at worldwide installed wind power, it's been growing at an average annual rate of about 21% over the last 10 years. And we now have about 500 gigawatts of installed wind power. Okay, now let's look at a couple countries. So which country do you think has the most installed wind power? China, by far. Okay, so China has had an average annual growth of almost 60% over the last 10 years. And it now has about 1/3 of the world's installed wind power capacity. Now, what country do you think is second? No, not Russia. Wait, I heard it. No, it's not Russia, but I think I heard it. Someone said. United States is number 2. Okay, so the U.S. has had an average annual growth a little bit larger than the global growth. So 10 years ago, U.S. was number 1. China overtook the U.S. in 2011 and hasn't looked back. So China has about twice the installed wind capacity compared to the U.S. All right. Now, so that's comparing installed capacity. Perhaps another way to measure, wind is to look at what's called wind penetration. And wind penetration turns out to be a little more indicative of the challenges on the grid. Okay, so what wind penetration is by country here is the percentage of each country's electrical energy needs that's being met by wind. And here, Denmark is by far the number 1 on this measure. So in Denmark, almost 45% of their electrical energy needs annually is being met by wind energy. And these are percentages as measured across the year, averaged across the year. And so instantaneously across any particular hour, the wind penetration can be much higher. So in Denmark, they do reach 100% wind penetration multiple times a year, in which case they're trying to export their wind power to neighboring countries that can better use that power. So China, despite its very large installed wind power capacity, is only at about 4.5% wind penetration. And the US is only at about 6.5% wind penetration. So globally, about 4.8% of the world's electrical energy needs is being met by wind. So overall, wind penetration is not too high, but there are countries which have more than 20% wind penetration. All right, now how does wind energy work? So I brought a little model of a wind turbine that I thought would be fun to pass around. Okay, so the base of land-based wind turbines is a lot of concrete. Okay, then we have the tower. So utility scale wind turbines for land-based turbines are typically 1 megawatt to 5 megawatts, and the towers are usually about 90 meters tall. Okay, so this will end up being about a 1/300th scale model of a utility scale wind turbine. So at the top of the wind turbine, we have the nacelle, which houses the drivetrain and the generator. And then we have the rotor with the hub at the center and the blades. So I'll pass this around just for fun. All right, so the way wind energy works, in a nutshell, is that wind comes into the rotor plane, and then due to the aerodynamical design of the blades, that creates lift that causes the rotor to spin. That will spin the low-speed shaft, and then that speed is typically stepped up through a gearbox to a high-speed shaft that spins the generator, generating electricity, which is then put on the grid and transmitted to users. Now, the operational goal for wind turbines has traditionally been to try to maximize power generation. So the control goal, as we design controllers for wind turbines, is to try to have the wind turbine operate as aerodynamically efficiently as possible and try to maximize that power generation. An additional control goal is to try to reduce structural loads on the wind turbine so that we can minimize maintenance issues and maximize the lifetime of the wind turbine. But I'm not going to get into details of particular control algorithms here. All right, so that's looking at wind. Now let's take a look at solar photovoltaics. Now I'm not really an expert in solar photovoltaics. I've only grouped that here into this talk because some of the challenges we have as we have more and more wind on the grid is very similar to the challenges of having more and more solar PV on the grid. Okay, so where are we in terms of solar photovoltaics? And I'm sort of separating out solar photovoltaics from all of solar. Solar photovoltaics happens to be the large majority of existing solar. And it's solar photovoltaics that has the same particular commonality with wind, which we'll talk about in a little bit. Okay, so this is the same graph that I showed earlier showing the growth of wind, and I'm going to add on the growth of solar PV onto the same chart. So the things that you should try to remember are that the average annual growth rate for installed wind ranges from 20 to 60%. Okay, so now if we take a look at solar PV, so worldwide, solar PV has grown at an annual growth rate of about 48%, so much higher. So there's now about 300 gigawatts of installed solar photovoltaics, and so that's about 60% of the worldwide installed wind power. Okay, and since we had China and USA earlier, we'll do China and USA here as well. The average annual growth rate of solar PV in China is a whopping 113%. And in China now, so I'm plotting the solar next to its corresponding wind. And so in China, the solar PV capacity now is about 40% of its wind power capacity. And in the US, the average annual growth rate is a little more than the worldwide growth rate. And now the solar PV capacity in the US is also about 40% of the US's wind power capacity. So if wind power capacity continues to grow at its average annual growth rate and solar PV grows at its annual growth rate, solar PV will overtake wind in about 3 years. Okay, so here for solar PV, I included China and US because we had those earlier. But which is the number one country in terms of solar PV? It is China. And look at that whopping growth rate, right? What is the number two country in terms of solar PV?
Germany.
It's not Germany. Germany's number 3. US is number 4. So who's number 2? This is a little surprising to me, too.
Sweden.
It's not Sweden. Sweden per capita does pretty well. Any other guesses? It's in Asia.
India.
It's not India. India's in the top 10, but not number 2. Japan. Japan is number 2, believe it or not. It moved into that position just in the last couple of years. All right. So now let's look at solar PV penetration. I couldn't find a similar chart as for wind, so what I did is I looked up the information, I was able to find it, and then augmented it onto this wind penetration chart. Okay, so combined wind and solar PV penetration is 15% or more in a number of countries now. And penetrations are increasing. With increased wind installations, increased solar installations, these combined penetrations are increasing, and it's expected that many countries will increase beyond 15% fairly soon. All right, now how does solar PV work? So I know much less about solar PV, so what I'm going to explain is pretty much all I know. All right, so PV panel consists of multiple layers, and there are different technologies, but kind of the simplest is just 2 layers where you have the semiconducting material, and typically one layer is biased or doped such that it's slightly positive, and the other layer is biased or doped such that it's slightly negative. And there are materials that where the photoelectric effect applies, so as the sun shines on it, photons hit the electrons and cause them to be free, and then because of this voltage difference across the layers, the electrons travel, and basically that generates electricity and is put on the grid and distributed to users. Now, the goal for solar PV, very similar to wind, is to try to maximize power generation. Okay, and so a lot of the studies involve materials and how to design the junctions to try to maximize that power generation. Now, simple lower-end PV cells are fairly inexpensive, but they're not very efficient. They're only converting some 10 to 15% of that solar power to usable electrical power. There exist higher efficiency solar cells commercially, but they also tend to be much more expensive. And then in research labs, they've demonstrated much higher efficiencies, and the challenge is to convert those technologies to mass production at a reasonable cost. All right, so wind and solar provide wonderful opportunities to meet our growing electrical power demand, and of course they're clean energy and can sort of mitigate climate change. But why is it a problem to have more and more wind and solar PV on the grid? Well, let's take a look at this balance here again, right? So as we have more wind and solar on the grid, they're added to the generation side, well, wind and solar are variable resources, right? There's only wind power available when the wind is blowing. There's only solar power available when the sun is shining. And so there's some uncertainty there. And by adding uncertainty now to the generation side, that makes it a little bit harder to balance things. Now, on top of that, wind and solar PV arrays are typically decoupled from the electrical grid through their power electronics. What that means is they operate independently of the grid frequency. So traditional generating plants have these large synchronous generators that are directly coupled with the grid. So as the grid frequency varies, these traditional power plants will react in a way as to try to balance the grid frequency. I'm not going to get into the details of that, but they're coupled to the frequency and they have some natural mechanism to try to balance the grid. Wind and solar don't, because they're decoupled from the utility grid. And so they operate independently of the frequency. They don't provide any balancing services. So as long as wind and solar PV are just a small percentage of the grid, a few percent, 5%, then it's okay. The remaining generating units can do all that balancing and it's fine. But as we're getting to higher and higher combined wind and solar PV penetration, we're getting to 10, 15, 20, 30, 40%, having that smaller and smaller amount of traditional generation is becoming very, very challenging in terms of balancing that grid. All right. And then furthermore, as I mentioned, as we have, say, more and more electric vehicles, we oftentimes will have sudden increases in electrical demand that also create challenges in balancing the grid. All right, so let's take a look at the typical system load again and see what happens when we have wind energy and what happens when we do, as is traditionally done, we take all that wind power that's generated. When the wind's blowing, it's free fuel. We want to try to maximize the wind power generated, and then we want to take it all onto the grid. And we'll reduce the system load then by that wind power that's generated. And then we want the remaining generating resources to meet this remaining load. And I've decreased things in a typical way where there usually is more wind at night than during the daytime. So now we want the remaining generating resources to meet this reduced load. If we have the same mix as we had before, we see that we're not only making gas cycle up and down, we're making hydro cycle up and down, and we're also requiring coal now to do some cycling. Now, large traditional coal plants are not designed to cycle up and down, certainly not very quickly. So that's a challenge. And you can imagine as we have more and more wind, higher wind penetration, that we might at some point want nuclear to do some cycling, and large nuclear plants are also not really designed to cycle. Now, newer, kind of small, modular nuclear reactors can provide some of those services, and there are newer, more modular coal plants that could also provide some of those services. Now, what happens if we add solar PV to the mix? If we also do the same thing as is traditionally done, when the sun's shining, you're trying to maximize solar PV power generation, you want to take it all onto the grid and then reduce the load from there. And so there's solar just in the daytime, and we take all of that. So now we reduce that system load, and this is what the remaining generating resources have to meet. So again, if we have the same mix as before, we see there's just more cycling up and down. And in particular, we see that there's kind of this sharp, steep increase here, and that's usually what's very challenging for the utility grid to meet, is this sudden increase in power that it needs to generate. Now, the system load we started out here with was fairly representative of maybe what happens now, maybe over the last 5 years. There was a little bump at the end of the day, end of the workday. Now, as there are more and more electric vehicles on the grid, oftentimes what happens is there ends up being much sharper increase at that end of the workday. And that will add additional challenges there. Okay, so what should we be doing differently? Well, I'd submit that trying to maximize power generation all the time is not really the way we should be controlling wind turbines. And trying to maximize power generation for solar PV panels is also probably not the way we want to be controlling solar panels, in particular as we have higher and higher penetrations of wind and solar PV. And so I'm going to talk about one particular solution that my group has worked on, and what this is called is active power control of wind, and similar ideas can be applied to solar PV. And the idea is that instead of always trying to maximize power generation, we want to derate and operate at some lower level on purpose, so that we allow ourselves some operational reserves within wind and solar PV. And then what we want to do is, actually control the wind turbines and solar PV panels we want to actively control the power generated from wind and solar to follow power reference commands that are designed to help balance the grid. And so we've been working in the wind side of this for a few years, where we've developed different controllers to actively control the power output of wind turbines. And I'm not going to go into the details of those, but let me just show you some field test results, where we've done testing on a 550 kilowatt wind turbine that's at the National Renewable Energy Laboratory, which is just about 10 kilometers south of our university. So ideally, of course, we don't want any frequency deviation, but in practice, there's going to be frequency deviations. There will be events such as this one where the grid frequency has dropped. So when grid frequency drops, what do we need to do? Do we need to increase power generation or decrease power generation? We need to increase power generation, right? And so the rated power of the turbine is 550 kilowatts. We derate by 10% so that we have this operational reserve, so that when this grid frequency drops, we can increase the commanded power to respond to that frequency drop. And then we want to control the actual power generated from this turbine to follow this commanded power, and we've shown that we can do that quite well. In fact, through numerous tests and various other research groups working in this area, we've shown that wind can actually be faster than conventional synchronous generating power plants in responding to these grid needs. Now, similarly, tests have been done for solar PV arrays. So this is not my work, but my colleague, Dragan Maksimovic, he's a professor in my department, he and his student, Andy Hoke, have done this field test just last summer, where they did this test also at NREL, and ideally there's no frequency deviation. Here they let the frequency drop quite significantly and over a short period of time, and Andy ran this test, so he decided to have a very aggressive input. Now, he has a solar irradiance sensor on site that he can estimate the total possible power that he expects the PV array to provide, and then he derated by 30%, and then he computed what the commanded power should be to react to this frequency drop. And it ends up that the commanded power actually increases well beyond the maximum that he thought he could get out of the PV array due to the solar radiance at the time. But he went ahead and commanded it and showed that as long as there's enough power available, he will follow that commanded power well until he reaches that limit. And he did a number of tests and showed that as long as there's enough power, solar PV can also provide faster responses than conventional generation.
So after the control version of it, does the frequency deviation then go back to zero, or?
So, yeah, so yes, in principle, if it could go all the way up, it would go back to zero. right? But we were just using these frequency inputs as inputs into our system. Yeah. All right. So now extending the control, active power control of solar PV, of a solar PV panel to a solar PV array is actually, is actually fairly straightforward, because solar radiance on one panel is about the same as the next panel, and the PV panels don't really interact with one another. Unfortunately, extending from one wind turbine to a wind farm is actually much more complex, because wind turbines actually interact with one another. So as this lead row is extracting power out of the wind, it creates wakes. In the wake, the wind speeds are lower and more turbulent, so the rear turbines don't see as much wind, can't produce as much power. They also see more turbulence, so they end up experiencing larger structural loads. And so it becomes very difficult to predict how these wakes will develop. It depends on atmospheric conditions as well. And so then active power control of a wind farm is much more difficult than active power control of a single wind turbine. And so this is ongoing research. A number of groups, including ours, working on this. We're working pretty closely with atmospheric scientists on this to better understand how and when wakes develop, and how can we then coordinate the control of the wind turbines on a wind farm to follow a power reference signal given to that wind farm. So there are many other challenges as well, but maybe just one other one to point out, which some of you might have thought of, is that we need proper market incentives in order to have appropriate active power control. Because how are you going to convince a wind farm operator to derate if they're going to lose that bulk power revenue? So you have to incentivize them. They have to be paid back when they provide their grid balancing services. All right, so there are a number of other possible solutions to having more and more wind and solar on the grid, but I'm running out of time, so I'm just going to list these. Obviously, we can curtail wind and solar as needed, but we don't want to do that too often because they're clean energy sources. Having more transmission lines can help, because we then transmit power to where it can be used better. Wind and solar forecasts are improving, and so that helps to schedule wind, solar relative to other traditional generation sources. As Christos already mentioned in the question to the previous speaker, demand-side management is another very active area of research. So I talked about traditionally, utilities try to control generation to follow the varying load. The idea of demand-side management is to try to control that load in some way. Try to not have everybody plug in their electric vehicle at the same time. And then storage, of course, is going to be part of the solution. It's still very expensive, but prices are coming down, and ultimately, it's going to be a combination of these solutions that will be the right solution for different situations. And so even though there are many challenges, there are many solution possibilities, there are very promising results from many of these solution possibilities, and we do believe that ultimately it will be possible to have 100% renewables on the grid reliably. So then just to end, I'd like to acknowledge our funding sponsors for their support. I want to thank many collaborators I've had in the wind energy area. They've taught me a lot about various aspects of wind energy. The collaborators in particular that I've worked on active power control of wind turbines and wind farms are on the left. I've had a great group of students. This is now, I guess, a pretty dated photo. Nearly everybody has graduated. The three students who have worked on active power control of wind turbines and wind farms are Andrew, Jake, and Peter. Over this last year, I've actually been on sabbatical, and I've spent about 8 months in Germany at the Four Winds Center for Wind Energy Research. And a few of my students actually also partook in research exchanges there. So Misha Sinner, one of my current students, he's actually still in Germany, wrapping up and returning to Colorado next week. Our host was Professor Martin Kuhn, and I also had the pleasure to work with Vlaho Petrovic and Mehdi Vali, who we've worked on active power control at the wind farm level. And I want to thank Professor Ho for all of his support and encouragement over the years. I think I first contacted him when I was a PhD student as I was finishing up. My then fiance, now husband, was at Harvard doing his PhD, so I contacted Larry about getting suggestions of companies to apply for jobs in the area. And he was nice enough to respond and give me a number of suggestions. The oldest photo I could find with both Larry and me, and it is from the Japan-USA-Vietnam Symposium in 1998. So there's Larry, myself. So Andrew Alleen and I were kind of the young assistant professors the peons of the group, but it was a quite distinguished crowd, including Professor Ho, so Pramod Karganakar, Masayoshi Tomizuka, Dave Auslander, Stephen Boyd's back there, Dev Garg, and Kishan Beheti. I was lucky enough to receive an Office of Naval Research Young Investigator Award, and then I was assigned to a program, and it turned out that Larry was funded out of that program on a different project, and so we got to know each other a little further through program reviews. And that led to my spending a sabbatical at Harvard over 2001 to 2002, where Larry's one of my hosts. And the most recent photo I could find, because of it, is when my family spent some time in Beijing in the summer of 2012, and we happened to overlap with Larry and Sophia for a few days, and it was very nice to have dim sum together. And finally, sorry I went over, thank you for your attention.